All right, welcome everyone. It's a pleasure to welcome you all to this webinar sponsored by the Chicago DOE Alliance Center. Our speaker today is Professor Dana Freedman. Dana is the Frederick George Keyes Professor of Chemistry at MIT. Dana is an inorganic chemist who applies synthetic chemistry to address questions in condensed matter physics and chemistry. And this includes molecular approaches to quantum information science, as well as studies of structure and bonding and the creation of new materials under pressure, work that involves interactions or has involved interactions with CDAC over the years. Dana received her bachelor's from Harvard and her PhD from Berkeley. She was a postdoc at MIT before moving to Northwestern in 2012 and rose through the ranks to a full professor in 2020. And it was there that she began interacting with Steve Jacobson, a CDAC partner, and did work there as well as at HPCAP and elsewhere in high pressure. Dana has received many awards, including a 2017 Presidential Early Career Award, the 2018 Kavli Frontiers of Science Fellowship, 2019 ACS Award in pure chemistry, and most recently, it was just announced last month, she's a 2022 MacArthur Fellow. So this is our first MacArthur Fellow giving a talk in this series. So great, congratulations for that. So we're really delighted you're able to give this talk. We've been trying to arrange it for some time. So take it away, Dana.
Oh my goodness. Thank you for the kind introduction and the unnecessary reading of awards. It is really fantastic to have the opportunity to speak about our work on high pressure. I feel like I don't get the opportunity to talk about this work nearly enough. You know, I was really fortunate when I was at Northwestern to have such an amazing Earth and Planetary Sciences department to interact with. I was initially drawn in by all of the displays of rocks in the lobby, and then slowly began to stalk all of the faculty to learn more about high pressure research, which is something that has long been a fascination of mine. I'm going to talk about how we use high pressure synthetic techniques for chemistry. But before I talk about that, I'm going to focus on why we want to make new chemical compounds and what's exciting to us about this space. So it has actually been a while since I've given a talk on Zoom. I have been enjoying these in-person talks. Okay. So as the title indicates, I'm going to be talking about bismuth, which is my favorite chemical element. And this graphic is taken from an accounts article that we wrote a bunch of years back describing how we can explore a wide chemistry space using high pressure. And this should look like something straight out of Star Trek, where you're exploring the undiscovered areas of high pressure space. The article also has a number of Star Trek jokes in it. I think it's very funny, but I'm the only one who thinks I'm funny. Okay, so what do we want to do? Our core interest in creating new intermetallic compounds is being able to separate out the core elements that contribute to magnetism. And so just to orient us all to the same place, we have a magnetic moment, which is comprised intrinsically of spin and orbital angular momentum. Now, in something like a lanthanide, these come together and give us a J ground state. But in transition metals, we're used to defining our magnetic moment as spin, right? Not J. So we say something as S equals 5/2, for example. So what happened to the J? Now, in transition metals, we fundamentally quench this orbital angular momentum. And you can envision that very simply, because when you apply a ligand field and you localize your electrons into your respective d orbitals, none of the d orbitals look like this, right? None of the d orbitals are fundamentally your orbital angular momentum. And more technically, since I know that I have a fantastic interdisciplinary audience, more specifically, you need electrons that are housed in the orbitals that comprise the orbital angular momentum the same orbital angular momentum quantum numbers. You need the L plus and minus 2, for example, combination to be potentially occupied in order to get this circulation around the nucleus. Okay, so we quench orbital angular momentum with the application of a ligand field. So what that means is that transition metals are fundamentally spin only. Now, how do spin and orbital angular momentum couple together? How do we get something that has a lot of orbital angular momentum? So spin and orbital angular momentum couple together relativistically. Nominally, it's z effective to the fourth. It's a lot closer to z effective squared in reality. But from a first approximation in a hydrogenic-like atom, you get that spin and orbital angular momentum couple as z effective to the fourth, which simply means heavy elements have a lot more orbital angular momentum to contribute. So if we want something that contributes just a spin moment, we can think about a lot of things. We can think about iron, we can think about manganese, and we can assume that we're going to have this nice spin-only moment. Now, let's say that we want to perturb this and we want to get into a space which is actually theoretically hard to explore. And I'll admit that talking about spaces that are theoretically hard to explore while Roald Hoffmann is on my screen does make me a little apprehensive, but I'm going to continue to say it's theoretically hard to understand the structure of things that have a lot of orbital angular momentum and spin. So with that said, if we want something that has a ton of orbital angular momentum, we want a heavy thing. And these heavy things that add in orbital angular momentum can perturb our spin moment, but they can also contribute to other forms of properties overall. So for example, let's say that we have a conductor and we want to see how orbital angular momentum perturbs the conductor. You can imagine bringing together, for example, copper and bismuth and seeing what'll happen. Getting access to this space is potentially really exciting for chemistry. So I've already said what we're going to do, but I'll say it again. The heavy thing that we want is bismuth, which is nominally the heaviest element that's stable to radioactive decay. It does decay in slightly longer than the age of the universe, which means lead is technically the heaviest element that's stable to radioactive decay. But bismuth is this fantastic element where we can imagine taking a single element that has a well-defined property, adding bismuth to it, and then creating a new host of properties. In the magnetic arena, you can imagine taking bismuth as a source of orbital angular momentum, taking another element such as iron as a source of spin, and uniting the two to create effectively a total magnetic moment, which is split up over two constituent atoms. The problem is, and we know this because this is a high pressure seminar, the problem is that these combinations of elements don't exist. And so if we want to create new binary compounds, and binary compounds are compelling because we can actually study the fundamentals of these materials. So if we want to create new binary compounds, then what we want to do is access the space that hasn't been explored. The binary phase diagrams have been worked out for 100 years. If iron bismuth doesn't exist in one of those, then we need to access spaces that are beyond the traditional thermodynamic spaces. And so just as two reminders, right? The first is, if we're accessing metastable materials, that doesn't mean that we're making unstable compounds, right? Diamond is metastable, graphite is forever. We know this because it's a high pressure seminar and we've all heard this a million times. The other thing is that even if we access materials with a thermodynamic variable such as pressure, we're pushing into a kinetic regime once we decompress and move into a regime where that minimum that we've created is no longer the global minimum. And so we really have to use vectors that push us past standard thermodynamics in order to create new materials. So the vector that's been most successful for us and for pretty much everyone, I assume, on this Zoom, oh my goodness, there are 70 people. There were 4 the last time I checked. Okay. The vector that's been most successful for us is high pressure synthesis. And high pressure synthesis. In particular, we have been using diamond anvil cells to create pressures that are comparable to the cores of planets, specifically Mars in our work, but others have reproducibly reached pressures of the Earth's core at about 360 GPa using diamond anvil cells. And so as a trained synthetic chemist, I love diamond anvil cells because when I do solid state reactions in a furnace, it's terrible. You literally put your materials into a black box and you stare at it and you get angry, or I do. And you can't see what's happening. You can't understand any of the process. Whereas in a diamond anvil cell, we have these beautiful, tiny, transparent reactor vessels. And from a synthetic perspective, this is incredibly compelling. So, if you're doing solution phase chemistry, you monitor your reaction as it progresses. You can monitor it by taking NMR time points, by measuring IR, even by looking at PXRD, if it's appropriate. Whereas with solid state chemistry, you have no probe that goes into a furnace in a meaningful way. Diamond anvil cells get around that problem, and you can access a wide range of temperatures and pressures and start to understand what's happening in your reaction. And to me, that's incredibly valuable. For those of you who haven't played with diamond anvil cells extensively, here is, just for scale, a diamond anvil cell on a goniometer head. So this is something that you literally hold in your hand. Okay, so we have our goals to introduce orbital angular momentum to things with bismuth. We have our vessel, which is a diamond anvil cell. What are we doing? So in the approximately hour, I'm going to talk for less than an hour. I want there to be significant time for questions. I'm going to talk about how we can use this for the original purpose I discussed, which is making magnets, how we can consider using orbital angular momentum as a vector for creating topologically non-trivial new materials, and then ways that we can use theory that even a synthetic chemist such as myself can use to predict new phases. And I'm briefly going to talk about something totally different, which is how we can use pressure to access spin liquids. Okay, so let's talk about pressure overall. So one of the first systems that we went after, and this is terrible, I would tell my students not to give a talk this way, but the truth is one of the first systems that we went after looking for high pressure binaries was the copper bismuth system. And we went after this system for two reasons. One is right here we have this nice phase diagram where we're looking at the atomic percent of copper versus bismuth and temperature. And here we see that we have this liquid region where copper and bismuth mix like water and ethanol. And so because of this mixing region, we hypothesized that we could use relatively low pressures to access a copper bismuth binary compound. And as you can see, there are no vertical lines in this diagram that would denote the existence of a phase. So, okay, we have copper bismuth. One reason that we went after is we thought it would be easy, just what I just said. The other reason that we were excited about this is we believed that a copper bismuth binary was likely to be a superconductor and likely to have potential for additional interesting superconducting properties. So let's talk about copper bismuth. So instead of the temperature composition phase diagram that I showed previously, now we have a temperature pressure phase diagram. And what you can see, because diamond anvil cells are transformative and amazing, these cuts that we can take across the bismuth phase diagram demonstrate the temperature ranges that we were able to measure in different diamond anvil cell experiments. And so that color scheme will translate into the diffraction patterns that I'll animate in a minute. But our hypothesis in choosing these specific pressure ranges was that what we wanted to do was progress along the boundaries between the bismuth-bismuth phase transitions and see if those transitions were a fertile point for the synthesis of new materials. Okay, so these are the powder patterns that correspond to those cuts. And for any solid state chemists that are here, isn't this amazing that we can just watch this temperature range and collect the diffraction data and watch how when we pass over transitions, structural transitions between the bismuth 3 structure to the bismuth 5 structure, for example, we have the potential for the creation of a new phase. For those of you, if there are any in the audience who aren't used to looking at this, I'll just note that these Roman numerals refer to a different structure type rather than oxidation state. Okay, so we have our powder patterns, and the patterns at the bottom, which should match the color at which they were found, denote 2 new bismuth copper structures. And so here we have, and this is work done by a former student of mine, Sam, who's now staff scientist at Livermore, still working with high pressure. So we have copper 11 bismuth 7, which is the first copper bismuth binary that was discovered. And this compound shows a lot of interesting structural motifs, which you could get into for hours, or well, I could get into for hours. For example, if you see these aren't technically channels because they're not porous, but the columns, which I'm going to assume you can see my mouse. The columns that are formed by these 6 bismuth atoms, you can see that the arrangement of them is very much supported by the protrusion of lone pairs into this non-channel structure, into this column. And another feature, which to me is fairly notable, is that the bismuth and copper local structures segregate into more bismuth-rich regions and more copper-rich regions. We also have this copper-bismuth 1-to-1 binary compound. I don't know why that happened. Okay. We also have this copper-bismuth 1-to-1 binary compound where you can see that we have these nice layers that are separated by these van der Waals interactions between the bismuth atoms. And these, to me, look fairly promising for future exfoliation studies. So we have these 2 compounds, and not only were we able to synthesize them in a diamond anvil cell, we were also able to access these materials in a multi-anvil press. So I've literally held both of these compounds in a gloved, hand, and they persist to over 100 Celsius in a DSC experiment. Okay, so we have chunks of these materials, and what we're looking for are what properties can we access with high pressure synthesis. So, so we made them in a map. Okay, so one of the first things that we want to look for is superconductivity. And here we have resistivity versus temperature. And for superconductivity, one of the features that we can look for that's indicative of superconductivity, indeed the hallmark of superconductivity, is a transition to zero resistivity, which is magnetic field dependent. And so as we increase the magnetic field, what we see is that the Cooper pairs that comprise the superconductors start to break and preferentially align with the magnetic field rather than each other, leading to the superconducting transition moving to lower temperatures. And so this material clearly demonstrates that. And I don't have it here, but heat capacity data, I mean, I don't have it in these slides, but heat capacity data are also indicative of a bulk transition in this material. Okay, so we've shown that we can use diamond anvil cells to scan phase space and to figure out where we can find new phases, and then we can replicate those phases in a multi-anvil press and acquire properties measurements. Okay, so that's cool, and that's an excellent first, in my opinion, and that's an excellent first step for looking at bismuth chemistry. Now, as I mentioned at the beginning, one of the key goals in this area is the question of what happens when you take an atom which is spin bearing, like iron, an atom which is orbital angular momentum bearing but has no spin, like bismuth, and smush them together. Can you effectively reconstitute a total magnetic moment over 2 atoms? And can you effectively use this as a design parameter to create both elements of a hysteresis loop? So the spin and the coercivity. can and bismuth, which is of course the best element. So if we look at the iron bismuth phase diagram, and here we've moved back to composition versus temperature, what we can see is that iron and bismuth barely mix with each other. They're more like oil and water rather than water and ethanol. So, okay, so we have our phase segregated compound. And what this told us is that we would likely have to try slightly higher pressures. So the pressures that you saw on the copper bismuth compound were about 5.6 GPa, comparable kind of to the core of the moon. Here, we're going to be looking at pressures that are more comparable to the core of Mars at about 30 GPa. And so by using a diamond anvil cell, we were able to create the first iron bismuth binary compound. And this is work done by a former postdoc in my lab, James Walsh, who's now at UMass Amherst. I think his picture will pop up in the near future. There's James. This is the aluminum 2 copper structure type. And what you can see is that we have iron atoms that are directly bonded to, you can see many things, but one of them is that you have iron atoms that are directly bonded to bismuth atoms. And this is arguably the first example of an iron bismuth bond in a solid state compound. And to us, this is a really interesting question. Why does this structure form, and why do you have these iron bismuth bonds? One potential, and we don't know the answer, but one potential hypothesis is that the iron bismuth bonds are formed not because of the stability of the iron bismuth interaction, but rather a bismuth-bismuth interaction stabilizes the formation of this structure shown here. This bismuth-bismuth interaction, which is denoted in the 30 GPa structure, is actually shorter than the double bond in certain dibismuth molecules, which are an interesting analog for a lot of the bismuth chemistry. Okay, so I am not going to, in this recorded talk, show any data, which makes me sad, but seems respectful and reasonable. So we want to know if iron bismuth is a magnet, right? This is the whole point. Is it coercive? Do we have orbital angular momentum from bismuth incorporated into the into this material? So one way that you can measure that is with a magnetometer, but that's very technically difficult because you have this diamond anvil cell with all of these components that aren't fully compatible with a magnetometer, especially if you want to laser heat your sample. So another way that you can imagine doing this is you can imagine using a built-in magnetometer. So we've been synthesizing these compounds in diamond anvil cells. You can take ions and you can bombard a diamond ions and create a scatter shot of defects. One of those defects that you can create is the anionic nitrogen vacancy pair defect in diamond. And there you have a chemically insane species, which is buried deep within the diamond. And I say chemically insane because you have an S=1 sp3 center, fundamentally. Now, this is something that I find personally upsetting, but that's what it is. And the reason that this is stable is because the bonds that you would have to break to move this defect are carbon-carbon bonds, and you wouldn't create a more stable location. So effectively, in a more solid state terminology, the low mobility of the defect in diamond is the reason that it's stable. That's also the reason that you can't get this defect too close to the surface of diamond. In the other half of my lab, we work on this problem, but for solid state work, this is actually miraculous. We have this tiny anionic nitrogen vacancy pair defect that we can put in the diamonds that we use to synthesize iron bismuth. So why do we want to do that? Why do we want to put defects into our diamonds? Or why do we want to pay De Beers a lot of money to put defects into our diamonds? The reason that we want to do that is because the anionic NV center in diamond can be used to optically read out spin information. And that's exactly what we want. This defect creates this electronic structure shown here, which you can use to optically pump and polarize, there we go, small polarize a 0.1 wave number energy difference with an optical wavelength, which is like 15,000 wave numbers. And then using fluorescence, you can read out the spin population. And so effectively, this is a magnetometer. Another way to phrase this is that you can read out the splitting between the M sub S levels, which means that you can read out your magnetic field. So if you know the initial condition, you know where your M sub S levels are, you know that your M sub S levels split predictably in a magnetic field by the Zeeman effect. If you can read out the splitting, you then know what magnetic field induced that splitting. And so in this way, these defects can be used as optical magnetometers. And there is significant work, which I believe I'm referencing on the next slide. I'm not. There is significant work on using these systems as magnetometers across systems. A number of scientists, including Norm Yao at Harvard, who we're collaborating with, have demonstrated proof of concept work that these defects in diamond anvil cells can be used to measure magnetic properties. So Norm did some really nice work measuring iron and gas things to look at because they're all calibrants that you can use to measure their phase transitions. And so it's a perfect way to calibrate the system. So we're collaborating with Norm on measuring this. So I'm not going to show you any data. I'm just going to say that we can integrate these things into, we can integrate diamonds that have defects into diamond anvil cells, and we can wire them up for microwave measurements. We can also compositionally map iron bismuth by powder diffraction. And by compositionally mapping this, what this means is that we can compare the magnetic map with the structural map, which is really powerful. And so we can effectively rasterize this space and measure the structure at every point and the local magnetic moment at every point to make sure that we're measuring iron bismuth. To be fair, since iron and bismuth are the only two things that go in and we already have the control data on the iron, we are fairly confident that we know what we're measuring. But I think that this is an additional really important control because measuring properties within diamond anvil cells is, as we all know, notoriously challenging. And so being able to correlate the structure map with the magnetic map is really important. So as promised, no data, but anyway, this is where we're going with a lot of measurements and something that I'm really excited to hopefully talk about in the future. Okay, so with that said, another way that we can access some of these data is by looking at systems that also are magnetic that we might be able to access under other conditions. So more precedent for using a magnetic moment tuned by bismuth to create permanent magnets arises in the compound manganese bismuth, MnBi. Now, this is a completely confusing, illogical system. It's a beautiful magnet. It crystallizes nominally in the nickel arsenide structure type, but it has all of these very weird properties. So for example, the hysteresis widens as you increase temperature, which is not generally observed in any material. So manganese bismuth and the magnetic structure was only determined within the past 5 years, I believe, with neutron data on a single crystal of this material. So manganese bismuth is fantastic, but it makes no sense. So we decided to continue exploring the manganese bismuth system to see if we could identify any other compounds that might shed light on the magnetism that bismuth can induce in a system. So in doing that, we created a new binary compound, MnBi2, that we accessed at high, as shown here, at 8 GPa and 700 Kelvin. And the promising thing about manganese bismuth is that we can actually measure it potentially. So theoretical calculations of this by our collaborator, James Rondinelli at Northwestern. James is just wonderful. suggests that this should actually be a permanent magnet. And again, I'm not going to show the data on that, but we are very optimistic that it is a permanent magnet. Okay, so I will transition from there to talking about completely different systems. I'm also going to look at the time because that seems to have disappeared from my computer. Okay. How do these work? Can I pause here for questions before I move to the next part to make this at least slightly interactive, or should I go into the next part? And Russ, it's okay if you've disappeared from the screen and you're not there.
No, that's fine. Go ahead. Are there questions? Simply unmute yourself. We have another 25 minutes.
And I have the other parts of the talk that I'd like to go in, but I don't know. I feel like listening to a Zoom for an hour at this point, I'm incapable. So I'd like to give everyone a chance to stand up and ask any questions that they might have.
How large are the diamonds in the diamond anvils?
How large are the diamonds?
Yeah, it's a silly question.
No. I'm just thinking like I can picture how big they are, but I don't have a good hey, Eric and Kathy, do you have a number?
Yeah, the culettes we use for most of our experiments are 300 microns in diameter.
Oh, sorry, I thought he meant the whole diamond, not the culettes.
Yeah, the table faces are 4 millimeters. They're about 2 millimeters tall.
2 millimeters. Okay.
And then the key part, as Eric mentioned, is the culettes. And so that's the flat face of the diamond. And, you know, mass over area, right? So the smaller you make them, the higher pressures you can reach.
Oh, okay.
And so the ones, so when you're talking about getting to pressures that are comparable to the core of the Earth, which is largely geophysics work and some work on high pressure hydrogen, for example, then you're talking about very small culet sizes and things that are outside of my area of expertise and highly controversial based on entertaining arguments of high pressure physicists. But at the pressures we're looking at, you know, 300 to 100 micron type systems.
All right, thanks.
Yeah.
More
You
questions?
can see them, which is kind of cool.
Yeah, that is cool.
And the other fun part, if you're not used to thinking about diamonds as a vector for chemical synthesis, ordering them is such a pain. Like, what do you mean you need diamonds as capital equipment? Yeah, okay. I've a lot more to say about that, but yes, that is yes. Christina.
Can I ask a question?
Oh, sorry. I just saw the hand.
Christina, would you like to speak up first?
Hi, Dana.
Hey,
Nice
Christina.
to see you.
Nice to
I
see you.
saw that you're giving an online seminar today, and I had a gap in my schedule. So great talk as always. I enjoyed it. Can I ask what other in situ techniques are you using to study the reaction process, basically, other than X-ray diffraction? Do you have other methods that you can do?
Yeah, absolutely. And so I would say that the entire point of the last part of the talk, if I make it there, is effectively a showcase of every technique we can use. So X-ray absorption spectroscopy, X-ray emission spectroscopy, Nussbauer spectroscopy, literally in a Nussbauer spectrometer, synchrotron Nussbauer spectroscopy, which is of course distinct from Nussbauer spectroscopy, Raman, FTIR, I might be missing something. I'm probably missing something. We have not yet done inelastic X-ray spectroscopy, but no, actually, that's not true. I think okay, anyway, pretty much anything that diamonds have such a wide window of transparency. Right. Oh, and like, of course, just UV vis spectroscopy,
Yep, yep,
yeah, eyeball spectroscopy, of course.
of course.
Um,
Yeah, very important. Yeah,
not
that's
for
great.
these
It's very,
compounds.
very impressive work.
Um,
Yeah, I especially enjoy the in situ characterization because you, as you pointed out early on in your presentation, if you do solid state reactions, it's more or less a black box, right? You kind of do this while your stuff is in the furnace, and
It's terrible.
yeah. So yeah, this is really great work. Thank you.
Thanks.
Okay, one more question, Trevor.
Oh, and there's a chat. I'm gonna.
Okay.
Oh my
I thought there was
goodness.
somebody before me, actually.
The chat is I
Right.
think that diamonds are considered consumables. That is, never tell my students that diamonds are consumables because they break them all the time.
That's how NSF and DOE classify them. Okay, Guy, did you have a question?
Yes, thank you. Great talk. But one thing that sort of bothers me and surprises me is how these intermetallic compounds are stable when you release the pressure. So is that, do you find a general phenomenon, or there were just some lucky few that those are the ones you're happening to be talking about?
Yeah, so I would say, so there are two parts to that question. The first is, do they persist outside of the pressures that you access them at? And the second is, do they persist down to ambient pressure? And so we found that everything that we've accessed at higher pressure persists down to pressures where they're not thermodynamically stable anymore. I would say about half of them persist down to ambient conditions. And understanding what changes are occurring in the bonding and to what extent we can count on kinetic stabilization, which is what you're doing when you're releasing that minimum, is one of the things that we're most interested in. Because thinking about how the bonds are changing when you release the pressure, that's kind of the interesting part, right? I mean, as you can potentially see by the graphic in the lower quadrant, we're working on predicting the stability of these phases. And now this is something that we can do in-house. It's actually, even for a non-theoretical person, it's not that hard to be able to predict what compounds will form. But what happens when you release the pressure, once you're under kinetic control, that's the hard part. So yeah, I would say about 50% of the compounds, and it really depends on the bonding. We have some hypotheses about the structural changes of bismuth and the bismuth 3 phase in particular, as it relates to decomposition. But I think that there isn't a good general rule that I would apply. There are general rules in the literature, such as the higher pressure you reach, the less likely you are to persist down to ambient. But I think I would be more comfortable with a deeper chemical intuition coupled to that. Does that
Okay.
get at your
Yeah.
question at all?
Excellent. Thank you very much.
Okay.
Okay, thanks. So why don't we move on? You have another 20 minutes, including questions.
Cool. Okay, I'll just keep talking and we'll figure it out. Okay, so bismuth is amazing. High pressure is amazing. I think that's where we've gotten to. So if, we want to actually look at the heaviest element that's stable to radioactive decay, we can consider extending to lead. And one reason that we might want to extend to lead, other than making jokes about radioactive decay, is that as we move from bismuth to lead, so one really interesting thing about these elements' properties at high pressure, and this is something that Roald Hoffman and others have studied, is that the electronic structures of individual elements change at high pressure. The orbital ordering changes. And when we move from elements to compounds, the electronegativity is going to change, and the fundamental electronic structure of a compound is going to change. So let's say that you have two compounds, you think you know their properties at ambient, you move them to high pressure. At high pressure, they fundamentally have a different orbital ordering. You combine them, and then you create an entirely new structure, which electronically cannot be immediately intuited from the parent elements. So why lead? So we're changing the electronegativity as we move from bismuth to lead. At ambient, lead and copper have almost comparable electronegativities. So what happens when we get into this space? And again, we are looking for materials that have interesting band structures that are influenced by the spin-orbit coupling. But one way to do that is to start to tune the electronegativity to create those structures. So my student Alex synthesized the first copper-lead binary compound, motivated by all of those factors. And what we find here, which we find kind of cool, is that if you look at the HCP structure of lead, which is the structure at the pressures we're synthesizing this material. We synthesize this at about 16 GPa. That structure becomes the stable structure around 13 GPa. We've found we cannot access this structure below that pressure. And if you look at copper, which maintains the same structure across the entire pressure range, you can almost envision this as an expanded lattice of the HCP lead phase interwoven with the copper units. We hypothesize, but have no evidence for this, that one reason that drives the structural formation is the comparable electronegativity of lead and copper in this space. But we have not come up with a good way to probe, the grand question of what drives the formation of one particular solid state structure. You'll talk to some theorists and they'll tell you, oh, it's all thermodynamics. But but thermodynamics is not an electronic structure reason. Yes, it's all thermodynamics, but you want to know where the electrons are, what bonds they're forming, and what are the electronic reasons why this is formed. But anyway, so we have this compound. This is another compound that nominally persists down to ambient conditions. I can talk about the acrobatics we went through to get it to persist to ambient conditions, but we can access it under ambient conditions. So again, the Rondinelli lab calculated the band structure and found these two potential crossings, which would lead to a potentially non-trivial non-trivial topology. So expanding the catalog of materials that have non-trivial topologies is interesting, especially in intermetallics, where we can potentially tune the Fermi energy to get closer to these band crossings. So that's something that we're kind of excited about. And we decided to continue along this quest to find a material. Oh, right. Sorry. We can tune the Fermi energy. The reason I mentioned we can tune the Fermi energy is it's obviously at the wrong energy here. Those band crossings are nowhere near the Fermi energy, so bad. Okay. So we can continue our exploration with lead and move from copper to nickel. And again, there are no binaries in the system. And if we want to measure physical properties, we should probably look not just at diamond anvil cells, but at the multi-anvil press. A schematic of the multi-anvil press is shown here. Here we can form materials that we can actually hold on to. And I should have been more specific with that earlier. When we have a diamond anvil cell, we're forming microscopic materials that we can probe in a very precise way because we know exactly where they are in the diamond anvil cell, and we can investigate that by pretty much any form of radiation that a diamond is transparent to. With a multi-anvil press, we have again a black box reaction, but we can form meaningful quantities of materials. And so when I said I can hold copper bismuth in my hand, I mean I can hold a chunk of copper bismuth in my hand and I can feel the weight of bismuth in that material. Okay, so this is a multi-anvil press. You take this tiny little octahedron, you embed it in this set of cubes, and you pay a lot of money for it, and then it breaks, and you put it in a multi-anvil press. For example, we've used the one at Argonne a lot. There's one at Brookhaven that we're using. And if anyone's on the line, I hear we're trying, my student Kathy, who I won't get to talk about enough at this talk, maybe next time, is looking to collaborate with Stony Brook on their multi-anvil press. Kathy is doing something awesome that is going to work soon with dynamic compression. Okay, so in situ data indicate the formation of a new phase, and we can envision the structure of nickel lead, which is the central structure, as on the continuum between the canonical nickel arsenide structure type and nickel indium 2. And you can see the change in the number of nickel sites along this continuum. And so this is an interesting question as to why these form and whether this simple explanation is indeed the explanation. The band structure here, shown a little bit better here, shows that the spin orbit coupling does create potential crossing points at the Fermi level, which could be the hallmark of a non-trivial topology, functionally meaning that the surface properties are different than the bulk properties. And that is promising. This is something that we're working on probing with ARPES, but we've had some pandemic-related difficulties. So we're very excited. And again, I'm sorry, these calculations are by the Rondinelli lab of the band structure. So I'm just going to check the time. So it looks like I have 10 minutes, including questions. Do you all want to do questions on this? And if you want one of the, you know what, is there any chance that I could get a show of hands in the participant window for whether you want harnessing theory to make new metastable phases or spin liquids? And I'll talk briefly about one of those and do questions. Spin liquids, hands up. Okay, and let's do harnessing theory to predict metastable phases. Okay, more on that one. And so we'll do that briefly and then we'll do questions. Cool. Okay, so another system that we were interested in for all of the reasons previously described is looking at 4D elements. So expanding the catalog from 3D elements to 4D elements. And again, we have, just like iron bismuth, for example, in the molybdenum bismuth system, an area where we see effectively a large immiscibility gap. And this is work by Allison and again, James Walsh, who's at UMass Amherst, and Allison has just started her position at Texas A&M, where she's going to be doing some beautiful high pressure research of her own. So, so if we want to do this, we could go in blind the way we did for iron bismuth. But actually, in the intervening years between creating that compound and where we are right now, there's been a lot of amazing theoretical work on creating programs that are, one is the Ayres computational method, where effectively we're sampling phase space and looking for local minima. And in doing this and applying this to this system, we were able to map out a number of potential compounds. And so what we're looking at here is the, again, atomic percent of bismuth and the enthalpy. And this is, of course, infuriatingly at 0 Kelvin. Because this is at 0 Kelvin, we're not just looking at, you can tell I'm an experimentalist, right? Because I'm complaining about 0 Kelvin. Because this is at 0 Kelvin, we're not just looking at the points on the convex hull, but also the points that are slightly above. Because within a within a given range of error, we expect that because we're doing this at high temperatures, that's going to perturb the thermodynamics of the system as well. And so what we identified right here is this molybdenum bismuth 2 phase. And we identified this at about 40 GPa. And so you can see that there are other structures that are less stable that we might find, but this suggested that 40 GPa could be a reasonable place to look for some structures. Okay. So we also observed a collection of other potential stable structures in these calculations. And what I want to emphasize is that this approach is really a guide for synthesis. And so this says, where do we see these different structure types beginning to stabilize and what compositional ranges are useful? Okay. So we went after the calculations and we found that there is indeed this molybdenum bismuth 2 phase. And this is an example of a compound that absolutely doesn't even come close to persisting at ambient conditions. Oh, sorry, I thought there was more on that. But anyway, we were able to perform calculations to predict and synthesize this new phase that does match approximately the structural parameters from the theoretical calculations. So yeah, okay. I think that is probably a good point to stop and ask for questions. And I will just move to my acknowledgement slide because my students do absolutely everything and they need to be acknowledged because they do literally all of the work that I showed. So I hope I've highlighted collaborators. Russ highlighted Steve, who's been a fantastic long-term collaborator. And I should have probably highlighted him more as well during the talk, but it's been absolutely wonderful to work with him as well, and all of our Beamline collaborators, but really my students who do everything. So yeah, I think I have about 5 minutes for questions.
Great. Thank you so much for a wonderful talk, Dana. Even without the data that you couldn't share, we look forward to seeing the NV center magnetic measurements shortly. Okay. Comments, questions, just unmute yourself, use the chat, or raise your hand. So have you been able to do many other multi-anvil experiments to sort of compare against the diamond cell experiments in looking at bismuth compounds, or has it been limited to just that one?
Yes, we've done a lot of multi-anvil cell experiments. I think that and we Kathy right now is doing some really nice work on the cobalt bismuth system. And we have been able to do a pretty good comparison between different measurements there. You know, what you're seeing is the fact that we didn't get access to national labs for a period of 2 years during the pandemic. So a lot of the multi-anvil work is really a little bit behind the diamond anvil cell work. And we've recently purchased a diffractometer that will enable us to do the diamond anvil cell work in-house. And so that should be really good for screening as well.
Mm-hmm. But also you can synthesize in principle, at least single crystals that can be used for refinements at ambient pressure. Your structures are probably fine, but you could get single crystal data from.
Oh yeah, sorry, I should have specified the nickel lead structure was single crystal data, for example.
Oh, okay, very good.
And the copper bismuth, I didn't get into the structure. It's actually super fun, but it's a modulated structure, copper 11 bismuth 7, and that is also single crystal modulated structure data, which is fun.
Okay, Sarah, would you like to ask a question?
Yes, thank you. And thank you so much for the nice talk. It was very interesting. And my question was about using theory to help you guide for the synthesis. Have you looked at low pressure I would say concave hull probably. Have you looked at that and see if that become a convex hull at a certain pressure? Could you interpret that? I mean, using those type of information.
Yeah, so we've looked at the decompression of these phases computationally, and that has not given us good insight on their decompression. I think that requires a more sophisticated approach, and it's one reason that we're really grateful that we get to collaborate with a number of wonderful theorists that we absolutely adore.
Thank you.
Roll, please go ahead.
I think you're muted.
Yeah, great talk. That was quite wonderful to see good solid state chemistry at work. I'm a little, in some of the structures, I saw some bismuth channels, it looked like. Have you, there are sort of two connected questions. One is, have you thought of putting something in those channels, alkali metals or something to perhaps to change the conducting properties? The other thing is just the sort of oxidation states 3 and 5. Yes, you didn't want to talk about oxidation states. But
oh no, the 3 and 5 were the names of the structure types, right? Not oxidation.
I know that.
Okay.
I know that.
I know you know that. I want to make sure. Okay, yeah, cool.
But let's take it seriously. The 3 and a 5. It's a fact of life with stereochemically active lone pairs for bismuth in certain oxidation states. So is there something, do you see some role for the lone pairs as structurally determining or as determining? I know you're interested mostly in intermetallics, but there are some interesting things about just compounds of which involve bismuth.
Yeah, so I'll answer the second question first. So yeah, we so from ELF calculations that were done by Chris Wolverton on the compounds that you're referring to specifically, we do see that the level of localization of the electron clouds that protrude into the channels and between the layers and the copper to bismuth 1-to-1 compounds are highly indicative of a stereochemically active lone pair. And so we do believe that it's the lone pairs that drive the structural formation. And I think that the lone pairs driving the structural formation is actually a great way to induce van der Waals interactions. And so the copper bismuth layered compound is something that we've been very interested for a while in exfoliating, because you can imagine that the copper bismuth 1-to-1 compound, ideally as exfoliated, could potentially be a topological superconductor. And so that's something that we've been interested in. We've had some synthetic challenges there, but this is something I actually chatted with your colleague, Seamus Davis, about for a while. I think that if we could get that compound into an STM, that would be really interesting. In terms of intercalating ions, yeah, so there's also a theory paper on the potential to intercalate ions in the copper bismuth 1-to-1 compound to perturb its properties. I think alkali ions are potentially interesting, but mainly as a vector to ease exfoliation. I also think that you might want to, so for example, the copper bismuth selenide compound, which is I don't know where the controversy settled, but which is a potential topological superconductor. I think thinking about that as a model and intercalating ions into copper bismuth in a controlled fashion could be really interesting to start to understand that space in some of these transport questions.
Right. Yep. Thanks.
Thank you, Rold. Christina, would you like to ask a question?
Yeah, hello. I enjoyed your talk. Thank you. I wonder, when you pressurize the two compounds and then you observe the formation of the new structure, is it 100% transition, or do you need a certain time, or do you need to increase the pressure, or?
Yeah, absolutely. So we watched the transition over time, and for all the things that I've shown you, we're both heating and pressurizing. And so one huge advantage of a diamond anvil cell is that you can actually measure across your sample. So your sample isn't homogeneous. And I haven't gone into the lovely details of these things. So for example, we use most commonly MgO as a pressure transmitting media. And MgO also, the convenient part about it is it has a very well-defined equation of state, which means that what we can do is we can use one laser spot and we can understand the structure of MgO and the structure of our material at that spot. So what it tells us is, at this particular spot, the pressure was this, and this is what compound you have. And so if in our little culet, we have this spot is iron bismuth, this spot is not iron bismuth, we can actually measure that across the sample. And so there's a huge difference. And this is one of the reasons, as Russ alluded to, that looking at the MAP experiments versus the DAC experiments is really compelling. In DAC experiments, you know, your finely ground powder is going to still be a 20 micron powder. And so you still have blotches as you move across your area. This is a really interesting challenge for thinking about ternaries, which is another area that we're kind of getting into quite a bit, because then you need 3 blotches that make a cross section. And so you obviously need a completely different strategy for doing that, because statistically it's not helpful anymore. So in a diamond anvil cell, you don't expect to get complete conversion because of your sample prep fundamentally, unless you go for a different form of sample prep. Whereas in a MAP experiment, you can expect more complete conversion, and there you can heat for you know, multiple hours as opposed to minutes. So you can heat for 12 hours and then you can get a more homogenized sample. In addition, in the MAP experiment, if you get past the melting point of a lot of these materials, then you're effectively running a high pressure flux reaction. And so that also will will be more amenable towards reaction completion.
And the opposite, when you take off the pressure, does time play a role here?
Okay. So with the copper lead compound, I tortured my poor student. So what we saw is time dependence, not the way you mean. We saw that the compound was slowly decomposing over time. Once we got it to ambient pressure, but we didn't have a lot of it. And my hypothesis was that it wasn't decomposing over time. It was that bismuth that was advantageously in the reaction was catalyzing a structural change by templating, because it was templating the formation of additional bismuth. So I got this poor student to actually try to figure out the time dependence of these reactions by taking a MAP reaction and shoving the whole thing into a PPMS and watching the properties change. I don't think we're ever going to be able to publish these data unless I torture another student into repeating everything. And now that the students all know what it took, I think it's never going to happen. But yes, for certain reactions, there is a time component. And I am confident about that. And is definitely worthy of further study.
Okay, thank you.
If I may make a comment, it's rolled. One lesson of the nanothread work was that the polymers formed on slow depressurization. Now, slow depressurization is what any solid state chemist, and Dana, you can confirm this, would recommend when you do a synthesis. You put it in a furnace and then you go away for 3 months, okay, while it crystallizes. But the people who are doing diamond anvil cell work at accelerators are under terrible time pressure. They have 2 days to work. They have no time to do things slowly. And it's not only for food and love, but also for high pressure. It really is good to do things slowly if you can.
We just bought a diffractometer where we can do all of these experiments in the basement of MIT. That idea was not lost on me. And I'm a big fan of the nano thread work.
Yeah, all good points. And with these tools now, we can look at a whole range of timescales from, basically months, years down to nanoseconds in terms of reactions or decomposition or stability on decompression or synthesis. So there's a lot of activity now at these light sources and elsewhere, looking at time dependence of various phenomena at high pressure. So that takes us to roughly 7 minutes past the hour. We should let you go. Dana, thank you for a thoroughly enjoyable talk. We had up to 75 participants, and we'll put this online so others can see it. So thank you once again for a great talk.
Thank you for the invitation and all of you for showing up to a Zoom talk. Amazing. Thank you so much.
Bye-bye.
Bye.